forgot to record. I just want to do a little show and tell for you today. And if we have some time, I'll chat about a few things. I'm going to skip this slide. So we've been talking about phase transitions for the last week or so, 2 weeks. And again, we've seen this diagram about a million times before, right? I don't need to go through this, right? We have this solid phase at low temperature, high pressure, gas phase at low temperature, high temperature, low pressure. We have this intermediate liquid phase. And then everything up here is this critical fluid that we've seen. And so I just want to mention today, I want to give you an example of that this is just a very simplified form of a diagram. And in fact, that there can be many, many more phase transitions within each of these groups, especially for a pure material. And in particular, in the solid phase. So typically, as far as I know, every pure material has one liquid phase, one gas phase, right? There's not really many different ways you can create a liquid or a gas. Right? They kind of all have the same orientation, the same properties. So there's not really a way you can make different types of liquids that exist. Imagine you have a different arrangement of the molecules in the liquid. So that doesn't happen. The same for the gas as well, right? The gas is just random particles moving around. There's not really any meaningful structure in the gas, nor is there really meaningful structure in the liquid, though there is some. But in a solid, right, a solid is particularly interesting, right, because what's the big difference between a solid, a liquid, and a gas? Very, very interesting question, right? How are they distinguished between each other? What makes a solid particularly special? And I just want to make a quick note here. Why are solids special? And in fact, if you go look in the curriculum for this department, in the graduate program in particular, next semester there's a solid state chemistry class. There's no liquid phase chemistry class, and this is basically the only gas phase class you'll ever take. It's not really a gas phase question. I'm talking about solids, not really a gas phase class. So why is it that we talk about solids in particular? What is so special about solids that distinguish them from liquids and gases? And there's a really, really simple physical reality about the difference between the two that makes solids distinct. Let me imagine this. Okay, imagine you have, let's just, again, I apologize that I have to use boxes to describe things. I know I'm probably driving you crazy at this point with boxes. But imagine you have a box of a gas. All right, so I'm just going to put some molecules in this box. All right, we have a gas. All right, good enough. This is a gas. Right, and so what can we say about that gas? Well, we can of course say that it's got a temperature and a pressure and stuff. But in particular, what I want to focus on in particular is not really the temperature of the system or anything like that, but what is different between a liquid gas and a solid in particular? Well, it's the denominator. In particular, it's the denominator of the Clapeyron equation, which is the change in the molar volume. The thing that really distinguishes between gas, liquid, and solid is the differences in density. Right, so we can certainly say that this system, right, we could say that this system has an average density, rho bar, right, and imagine now I take a part of this box, let me just fill it in a bit more, not a big deal, but imagine now that I take this box and I subdivide it into smaller boxes, right? So what if I take a little tiny box here, like on the edge here, right? And I zoom into that box. Right, I zoom in. Right, it's like Blade Runner where it says enhance and you go deeper and deeper without any loss of pure quality. And what do I see in here? Well, I see a smaller number of atoms, of course, because it's just a partial. Right? But there's some atoms in here and they're moving. And what can I say about this box? Well, I can say that it's at the same, right? If I say that this is some temperature and some density, then I can also say that this part of the box is also at this temperature and density, right? It's got the same average density. As the big box. Okay, so no matter how I subdivide my box, right, I can zoom into here, right, and do it again, and I get the same answer. Right? I'm not going to do that, but I could do the same thing and do this, and I get the same average density and temperature, and so on and so forth. Right? I can keep zooming into my gas, And as long as I have enough molecules in there, I see the same box. It's just a smaller box. Right? It turns out that not, so what this means is that the system is what we call translationally invariant. What that means is that I can move from one part of the box to another, but I can take this box and move it here, I can move it here, I can move it here, right? And I get the same result. Right? So this system is translationally invariant. Which means that the properties are independent of position. All right? Simple as that. Right? It doesn't matter where I pick in the box. I'll just draw a couple more. Right? I can make a box here, I can make a box here, I can make a box here. Right? Every time I make a box, I get the same results. Right? It's translationally invariant. Not only that, if it were three-dimensional, imagine instead of having a box, I have a sphere. Now this is really going to challenge you guys to draw. So imagine instead I have a spherical box. Right? And I put molecules inside of this box. Right? And this is, of course, at some temperature and pressure, or density. Right? And now what I do is I take a cross-section of this, a little sphere or a little cross-section of this sphere. Right? Maybe I chunk it like this. Right? I look at that little cut of it. Right? And if I look at that little cut, that looks like this. Right, it looks like a little snow cone of gas. Right, this has the same temperature and pressure as all well. Right, it's translationally invariant. It doesn't matter how I cut it. But even more importantly, is if I rotate this cut by a degree theta, and I now have a cut at some different angle, I see the same thing. All right, so what does this tell me? Well, it tells me that not only is the system translationally invariant, but it's also rotationally invariant. Right? I can spin my box in any degree, any rotation, right? I can make my cut any way I like in terms of angle or size, distance, whatever, and I get the same box out. It's a smaller box, it's got less molecules, but it's got the same temperature and the same density. Right? What's the claim here? Is that the system is homogeneous, right? Right? The claim is gases are homogeneous. Right? They also might be isotropic, but we won't worry about that, right? Which means that it's the same in all directions. We have to worry about attraction. But it's homogeneous by and large, which means that no matter how small your cut is, you have the same density. All right, so now let's think about the same idea, but with liquids. Right? What if we have a liquid in here instead? All right, what do we know about liquids? Well, imagine, so let's assume that this is fully filled with a liquid, so you don't have like a gas layer and a water. It is completely filled with a fluid, a liquid fluid. Right? You have a beach ball filled with water. The same thing applies, right? Water, right? Liquid fills the entire space that it can fill, and every droplet of water that you pull out of a bucket has the same density and the same temperature as the bucket, right? Very straightforward. Right? So liquids are also rotationally and translationally invariant. I don't even need to draw that. Also true, liquids are homogeneous and spatially or liquid or translationally and rotationally invariant. Right? It does not matter what the volume of the box is, just as long as all things are kept equal, you get the same density. This is true for solids, though. This is true for solids. Of course, there are many different types of solids, right? We have crystals. We'll think about crystals in a second. They're a little more complicated, even though they're the simplest form of solids, it turns out. But you guys are probably more comfortable with a more complex solid, which would be like an amorphous solid. Something that doesn't have a fixed shape. Something that looks like a powder, for instance. A powder would be a good example of an amorphous solid. Is this true for a powder? Right, and the way to think about this, so let me write this. I just want to do this for my notes, and I'm going to go to the next page. Okay, so what about solids? All right, so let's consider two different types of solids. All right, the first one I want you to consider is a bucket of sand. Okay, bucket of sand. All right, this is an example of an amorphous. Can I spell this right? Amorphous. I think that's how you spell it. If it's not, correct me. A solid, e.g. a powder. All right, so what do you do with a sand, right? So let's draw my bucket. So here's my bucket, my Charlie bucket. Here's my bucket. Not a very good bucket, looks more like a cylinder, but that's okay. And I'm going to put some sand in there, right? So I'm just going to draw a bunch of little dots, right? And there's lots of them, right? You have this closely packed powder of sand. Sorry, I've actually touched it so much that it's freaking out. There we go. Come on. Okay, let me save this. All right, so you have a bucket of sand, right? So we can look at this and ask the same questions that we did for the gas. Right, we can measure the temperature, right? We can measure that it has temperature. And of course, we can measure the weight of how much sand is in there. And we can measure the volume, right? So it has a well-defined volume and a well-defined mass. Right, so that means that we can calculate a density, right, which is equal to the mass of the system, the mass of the sand, over the volume of the sand. Okay, so that makes a lot of sense, right? We calculated a density. All right, so now let's do the same process that we did before. Let's take a small chunk out and then look at what we see. Right? All right, so let me just take like a small. How do I want to do this? Let's just do a same, like a little arc. All right, so we're going to take this little chunk out here. All right, so I'll draw it like this. And what do I see inside that chunk? Well, as you continue to zoom in, what do you see? Well, you see some of the particles are bigger than others, right? Some sand particles are very clearly quite large. Some are quite small, right? So you have some that are big, some that are large, or some that are small, some that are minuscule, right? They just look like little tiny grains, right? And some of them look like little crystals even, right? If you ever looked at sand closely, you'll notice that. Right? So there's a distribution of sizes. Right? So what if I take little chunks of this? Right? If I take this chunk right here, well, first of all, it measures the same temperature, but it measures a density. But if I take this chunk right here, right, where all these little particles are sitting, the temperature might read the same, but you measure a different density. Right? This is like the smallest. And this is the large particles, right? So in fact, what you're measuring in the original condition, in the original sand pail, this density here, this is not a well-defined density. Singular, it doesn't have a singular value, but rather it's an average, right? It's an average. And so there's going to be a distribution, right? There's going to be some particles that are larger, some particles are bigger. And on average, they average out to some average density. Okay? Is this rotationally and translationally invariant? No. Because it depends on where I cut out, I get a different density out, right? Maybe I cut a little part of my solid that just has small little particles in it, and then I cut out a different part that's got big particles in it, right? Different densities, right? If I take a bunch of samples and then take the average density, I'll get the average density I read out of the bucket, but you don't get the same continual subdivision and the same homogeneous nature that you get for liquids and solids. So this system is not invariant. Okay, and I'm going to show you one more example in just a minute of a different type of solid, a crystal. It's a little harder for me to draw that, so it's much easier to see this when I look at the crystal structure. But what we'd say here is that there's a there's a clear difference between a liquid and a gas, which, by the way, are the same phase at certain temperatures, and solid. Right? That's the reason why there's a critical point, in particular, between the liquid and the gas, because both phases are the same, have the same symmetries. They're not fundamentally all that much different, right? We've identified the difference between a liquid and a solid is that the liquid is in the intermediate region where the attractions between the molecules in the liquid beat the entropy, right? Beat the heat of pushing the system apart into a gas. Right? But there's really no fundamental difference between a liquid and a gas. It's just a slightly different organization of the molecules that exhibit the same symmetries. Right? So liquid and gases aren't really all that different. They're just kind of, liquid is just a side effect of attractions. A liquid's no fundamentally different than a gas in that sense. Solids are utterly completely different. Solids have a completely different symmetry. Right? So solids are, in some ways, an entirely different class of molecules or class of states because they don't show the same behavior. They don't show the same symmetries. Right? When you look at, for instance, surface chemistry, so if you have for instance, in like a catalytic converter, right? A catalytic converter in your car converts uncombusted gasoline or fuel and completes the combustion by using a metal surface, a honeycomb pattern of metal, so palladium, platinum, and titanium, I think, I forget off the top of my head, maybe chromium, that enables, that promotes and catalyzes combustion of the unreacted gases with the oxygen that flows through your exhaust. And it turns out that the effectiveness of these catalysts, imagine that what you have is a surface, like say you have a crystal, if you will, or some material that you cut a flat plane out of, right? You're going to place this plane of the surface, if you will, of a crystal or something like that. And so let me imagine it like this. Right? I want to cut out a little bit of a material and I want to place it in my converter as a surface, right? So imagine that I start with a block of metal. Let me erase this. I want a 3D box. Right, so imagine you have this cube of metal. Okay, and so this is the material I want to make my catalyst out of. Okay, and so what I'm going to do is I'm going to cut a slice of this through, right? And like I'm going to cut through bread. And I'm going to cut it like bread, and I'm going to take a slice out, and I'm going to put it in my converter as my catalyst surface, as my surface. Well, there's different ways to cut the square, the cube, right? One way I can cut it is I can cut it like a piece of bread, right? And I can cut it along the plane of the axis, right? This is like a bread slice. Right? I could cut it like that and make that my new surface, right? But I could but I could also cut it long ways. Let's see if I can draw this. right? Let me do a different color so it's clear. Right? I can also cut my system crosswise like this as well. Right? I could do something like this, like a diagonal slice instead. And of course, if this is not a cube but a rectangular box, whereas in this side is longer or smaller than this side, cutting along this side is different than cutting along this side because they're different surfaces. The one's wider than the other. So there's two different ways, for instance, on a cube here. There's a couple of different ways to do it as well, but these are the two that I'll mention. Are ways that I can cut this crystal, if you will, this box. And it turns out that in solids, in solid state chemistry, these two cuts have different reactivity, different properties, and reactivity. Right? I highly recommend you take solid state or advanced inorganic here in the department if you're interested in this concept. I obviously don't have time to talk about this. But it turns out because a solid is not translationally invariant, which means that different cuts have different densities and different properties. If I cut like a traditional loaf of bread down the middle and take that slab out and use it, it has different reactivity than if I were to cut the crystal along the diagonal. It would have a different system. It would have different reactivity. Right? You see this time and time again in catalysis. Catalytic, what do we call heterogeneous catalysis, which is where you have, say, gases and liquids reacting on a metal surface, like in a catalytic converter. You have to cut your catalyst metal in a certain orientation, and depending on that orientation, gives you different chemical properties. Some cuts absorb molecules really, really well onto the surface, and it's really hard to get them off, which is what you don't want, because that poisons your catalyst. You want your catalyst to flush. You want stuff to come on your catalyst and then leave. So if you cut it one way, it might be really, really sticky, but it's really hard to get stuff off. Right? And you poison your catalyst. But if you cut it along the diagonal, it might not be as strongly attracting, but it'll attract some, and it's also much less sticky, so it doesn't poison. Right? So people often, chemists, solid state chemists, spend a lot of time thinking about cuts, slices of solids, because the system's not translationally invariant. You get a different density of your material depending on which cut you get. Right? These each have different densities and structures. Right? They have different densities. P and 3 prime, rho and rho prime. Different densities. Okay, let me show you an example of this. So let's look at water. Okay, yeah. So this is what's called a unit cell of regular hexagonal water. That's the water you guys know, like makes snowflakes and ice. This is what we know and love of ice. It has this six-fold symmetric structure. Right? I'll show you a 3D picture of it in a minute. Okay, and so you can imagine now, imagine you have this cylinder. You have these layers of water stacked on top of each other like this, like a bunch of hexagons that are stacked like this. Right, you have this bread loaf of ice, if you will. Now imagine cutting it vertically straight down the middle. Think about what that cut looks like. Right. And then what you do is cut it a slightly different direction. Cut it along this axis instead. Instead of this axis, cut it another 20, 30 degrees or so. What do you see? A different surface. Right? You've cut through those atoms in a slightly different way. And so the density on the surface of oxygen and hydrogen atoms, the structure of it looks different, depending if you cut it like a bread loaf. Right? If we cut it in the plane of the board, right, you just get little concentric hexagons, right? If you cut it in the plane of the board, like a bread loaf. But if you cut it vertically or vertically down the center and out of the board, right, you get a different structure. Right? For liquids and water, liquids and gas, that doesn't happen. Right? It doesn't matter which way you cut through a gas or a liquid, you get the same thing. Same average density, same properties, same structure. But in a solid, in a crystal, or in an amorphous solid, you don't get that anymore. right? And a crystal, which is fixed, a fixed structure like this, right? And what a piece of ice looks like, let me just remind you what this looks like. This is what's called a unit cell. What this means is that water ice, the smallest structure of water ice, is one of these, okay? So a snowflake, if you will, is just a tiling of these unit cells. Okay, these little 6-member rings are just kind of tiling around, and they propagate in a 6-fold symmetric way because the crystal is 6-fold symmetric, hexagonal symmetry. All right, so this is basically the smallest. This piece right here, imagine you have like thousands of these populating the board that are all connected. The smallest subdivision that you can cut, where you get the same property every time you cut the ice in that way, is this. Right? Because if you cut this any smaller, you see clearly you get a different structure. If you cut this like a bread. Right? So this is a unique part of water, or a unique part of crystals. Crystals have this property, in the sense that they are only translationally invariant up to their crystal, their unit cell, which is this. Right? So water is subdividable. This is the smallest unit of subdividable water. Any smaller cuts give you a different structure. Okay, so crystals are special like that, right? Very, very different than a liquid. A liquid you can cut any way you want. Gas you cut it any way you want to get the same stuff. Right? Crystals are very different. Because of that, because there's not translational invariance anymore, there may be possible many different ways to arrange molecules in a solid. Right? Because they're not invariant anymore. There's going to be specific energies for specific arrangements, and some arrangements are going to be more stable than others. But there's no limit to how many possible translationally variant or crystal structures you can have. It all just depends on energy. So let's look at water. This is the water phase diagram. Fairly recent, and actually it needs to be updated a little bit. But this is a fairly recent thing. And again, we see everything that we expect to see here. Right? Let's just start at 1 atmosphere. Right, here's the triple point of water right here at 273, 0 Celsius, and 100 kPa. Right, that's our standard. That's our standard temperature and pressure. Here's the triple point here at 273.16 and 611 pascals. Excuse me. Right, and here's the liquid solid line, or the liquid gas coexistence line, from the triple point to the critical point, right? Liquid and vapor, everything you know and love. Nothing exciting here. But let's look on the left side here. The solid side is much more interesting, right? We have one liquid, one vapor, and then out here we're supercritical. So let's do what we do in our freezer when we make ice cubes. We take water here. Well, we take water here. We take water here at NTP, 20 Celsius, right? That's your coming out of your faucet. You put it in the freezer. You're at constant pressure in the freezer. You just change the temperature. So we move here, cool down, and it freezes out. So as we continue to cool into the ice layer, we form this ice called I sub H, which means hexagonal ice. That's what the H stands for, hexagonal. And so we end up getting this hexagonal ice. But notice if you keep cooling it down further. Right, some way we can push this ice even colder. We end up in a new ice form called I sub C. C stands for cubic. Right? Imagine now we take that ice, hexagonal ice, freeze it even more to really cryogenic temperatures, and we get a new form of ice, a new structure of ice, called orthorhombic, water 10, water 11. Or what if we take our water ice and then we pressurize it in an anvil, a diamond anvil, like homework 1, at constant temperature, drive it up. There's another phase transition into a new phase of water, solid water, water 9. And this is water 3 here. You see there's water 4, water 2, water 6, right? And you keep going. It's very, very complicated. Each one of these that I've mentioned here are all different arrangements of water in its crystalline solid form. All right? We know hexagonal ice because that's what exists at terrestrial conditions. But, and I'll show you again a picture of these. Right, here's hexagonal ice. This is what the water cell looks like, the water crystal looks like. If you had one crystal of water, it would look like this, single crystal. The cubic ice looks like this, right? It actually has it's not a 6-fold symmetric structure like a snowflake. It's a 4-fold symmetric structure like a cube. And in fact, this exists in cold places in the world, in the universe, or in the galaxy, not in the world. For instance, if there was snow on Jupiter, which there's not because too much pressure, if there's snow on Jupiter, it would be square ice, square snowflakes. The snowflakes would be square. Because at those temperatures on Jupiter, say Neptune, Uranus, Titan, some of the far planets where it's really cold and the sun's not there, the water's at high enough pressure and cold enough temperatures that hexagonal ice doesn't form, it forms cubes instead. And so water snowflakes on Jupiter, if they have snowflakes, would be cubes or squares, not hexagons. Very interesting. And so what happens is, so those are probably the most two interesting ones, but again, there's a bunch of really interesting structures that happen at really high pressures, right? When you start to really cram those waters together, really start to cram them together, things start to get very, very complicated. Here are some examples. Right, this ice 11, that's the one that was way down at low temperature at standard pressure. It kind of has a six-member structure, right? It kind of looks like the six-member rings in hexagonal ice, but the pressure is so high and the temperature is so low that it can't fit a certain number of molecules into the hexagons. There's not enough energy to kind of open these rings up to let these in. So water 9 has these extra kind of water sticking on the outside because the pressure and the temperature is so low and the pressure is so high that there's not enough entropy to fit them in. So they get kind of frozen out on the outside of the hexagonal ice. It still has the same six-fold symmetry, but you end up getting a slightly different density because you have these waters on the outside instead. As you really start to compress the ice really can't get into that arrangement that it wants to have, right? Because the ice structure, hexagonal ice structure, comes from the fact that on average, each water accepts or donates 4 hydrogen bonds. It's a tetrahedral. It's a tetrahedral water. So there's 2 waters like this that it's donating to if it's 2 oxygens, and it's accepting 2 from above and below in the tetrahedral form. And when you do that, you get hexagonal ice. Once you get to high pressure, the system is too tightly packed to get the water to arrange in this tetrahedral form. Right? So you end up making these kind of flat, kind of circular planes that have a symmetry of a rhombus at higher pressure. Right? Things start to flatten out, and they start to make kind of larger structures because they really can't orient with that high pressure into the arrangement that you have it at hexagonal ice like this. Right. So it turns out there are 18 of these phases. Water has 18 solid state phases that have been discovered so far. They've been known as far back as the 1940s, 1930s, but they've been discovered sequentially since then. This is the most recent one. This is water 19. This is the 19th one that was found. And it's actually a form of water 7 here, water 6. So let's see how they've actually created this. I find this very interesting. All right, so they start with liquid at about 25 C, right? So they start with liquid water, and they pressurize the liquid water across just at isothermal conditions, right, to about 1.7 gigapascals. That's a lot of pressure, as we saw in problem set 1. So they pressurize the system in an anvil cell, the water and then there's so much pressure that the water condenses, and at 300 into a solid, and at 300 Kelvin, you're not getting hexagonal water, because hexagonal water at that high pressure doesn't exist. Right? Hexagonal water is right here in this little corner at low pressure. Right here. That's all it is. Right? It's a very, very small section of the phase diagram. Water 6, in fact, in terms of pressure, takes up a huge difference. This is a very, very stable structure at high pressure. And so when you freeze this structure, so what they do is they pressurize it and then they cool it. They apply a cryogen to it to cool it isobarically. And the first place they stop is at water 6. That's what this looks like. And what you instead have, you have such high pressure that the system can no longer make these 6-fold rings. Right? And the 6-fold rings are ideal, right? First of all, 6-fold, as we know from organic chemistry, six-member rings are really stable. Hexane is really stable. Something about six-member rings that are really, really stable in chemistry. But the problem with 6-member rings with water is that they're kind of big, kind of large. The hydrogen bonds are long. And so at high pressure, you can't get the system it can't fight the pressure. right? So it can't expand into this six-fold symmetry, these kind of natural low-density ice that we have, because the pressure is too high. So in water six instead, it forms this square-like lattice where you have two different discrete sets of hybrid waters that form little individual squares, right? Each one has 5 waters in it. There's a little central water that's accepting hydrogen bonds from the other 4. So there's 1 tetrahedral water in the middle, and then 3 waters on the outside. And there's some connections along each of these different groups. And they're different colors because each of them have slightly different arrangements. So there's an alternating, it's basically an alternating crystal. You have one that's one type, one of the other type, and that one's the next type. Okay, and they mix together. And all together they have the symmetry of a square, right? So this is cubic ice, square ice. Snowflakes of this would be square. And you can see how tightly packed they are, right? The system isn't, each one of these, this is a bird's eye view of each one of these little squares, and you can see how tightly packed things are, right? Not the waters in the middle aren't really all on the same plane. They're all kind of crammed together, and it has this really tight waist, very long and stretched because the system is being compressed this way. Okay, so it can't fill that space that it will in regular ice. And in fact, this ice has much higher density than liquid. Okay, so dense ice. Now, what they do, get ice 19 is really interesting, right? They drop it with a cryogen, right? So they drop water 6, and then they supercool it with liquid nitrogen down to below 100 Kelvin to about 77 Kelvin, which is liquid nitrogen temperatures. And you see a similar structure, right? We call this a frustrated structure because it looks awful like water 7, right? Right? You have these groups, alternating groups of 6 waters, of 5 waters. But notice how the structures are slightly different. In the lower pressure ice 6, everything is kind of neatly arranged, right? Everything's nice and straight. Now, it's not ideal, right? We would naturally want this to form hexagonal ice where all the waters are tetrahedral, but it can't do that. So each little block, you get a tetrahedral water, and they're all nicely arranged in little squares. But when you're down here at ice 19, your pressure is really high, and you also don't have enough energy to stretch, right? It's too damn cold. There's not enough entropy in the system for it to kind of, smooth out and straighten out. So ice 19 instead has this, what we call a frustrated structure, which is where each one of these is just a little kinked and a little screwed up. Right? You can imagine that if I give this a little bit of heat, right? If I turn the temperature up on this a little bit, everything will straighten out, smooth out, straighten out, and you get this structure instead. You can just imagine, you just give them enough energy to wiggle a bit and do a little yoga, and you can straighten out to ice 6. But there's not enough heat in this system for that system to vibrate and to oscillate and to stretch out. So the system gets crunched together into this disorganized state. That's still a crystal. It still has the square symmetry that the other one does. But each one of the little units is crooked, equal and opposite to each other. Right? This one's tilted this way, this one's tilted this way, and so on and so forth. It's just alternating. Right? So we call this a frustrated solid. It's like a glass. So there's a sense of disorder in the structure. All these are all tilted, but it doesn't have enough energy to get out of that. There's not enough heat to replace this. So this freezes out. So we call this a glassy ice. It's not really a true solid phase, but it is in the sense that this is stable enough that it lasts a long time. It's a bit like glass. If you heat it up a bit, it's just going to relax over to the water 6, ice 6. Okay, so this was discovered just a couple of years ago. And this is the 19th. I imagine there are even more structures of water below this, but you really can't get past 2 or 3 gigapascals. So experimentally, it's hard to get past this point. What time is it? Okay, cool. All right, any questions about that? I really like the water stuff. It's very, very interesting. I want to show you one more thing about water today. So this is a really, really interesting argument from history that I want to talk about today. Just kind of close up our discussion phases. And one of the things that we talked about a couple weeks ago was that the third law, or the Nernst theorem, talked about it very briefly. which is called the third law, which says that as T goes to 0, S either goes to 0 for a perfect crystal or to a finite value. So that means that, so let's think about, for instance, what is the entropy of ice? Which is IH, hexagonal ice, at 0 Kelvin. What is this temperature? Right, so it turns out in the 1940s, people were finally able to start measuring this. And they do it by cooling water down and then extrapolating the entropy down to 0 Kelvin. And what you find, and they get this quite correct, quite accurate, is that the entropy of ice is 185.3 joules per Kelvin per mole. Okay. However, here's a really interesting thing. If you consider one crystal of IH water as having 6 water molecules frozen in place, theory predicts a different value. Right? What theory predicts is 188.7 joules per Kelvin per mole. Now this is a small difference. Right? So this says that there is an error in entropy between experiment and our theory of 3.4 joules per mole per Kelvin. All right? Where the hell did this energy go? Right? The experiment is missing an additional 3.4 joules per mole per Kelvin. Right? Originally, people thought that this was just rounding error, like this was experimental error, and people kept doing this experiment over and over again. Every single time they do it, they're always off by 3.4. Something systematic here is going on. And so it wasn't until the 1940s that people figured it out, this 3.4 Kelvin. And it's a beautiful argument. I'd just like to tell you guys about it just a little bit. It's very, very simple. And it uses the fact that, again, crystals, water crystals, are not translationally and rotationally invariant. They have, if you take a crystal and you look at it in one direction versus another, it looks a little different. So we're going to use the fact that ice is not homogeneous. Right? And this is an argument. This argument was made by a very famous chemist, Linus Pauling. I don't know if you guys know Linus Pauling. Linus Pauling introduced quantum mechanics to the chemistry classroom in America. He's the first quantum chemist. He won the Nobel Prize for it in chemistry, and he also won the Nobel Peace Prize for a different reason. Right? So he's one of the only people in the world, he might be the only person in the world to win 2 Nobel Prizes in 2 different categories. Right? Very, very famous scientist. And a genius at intuitive arguments about chemistry. Right? And this is what Linus Pauling's argument is. I'm going to go to the next page because I need a little space. Right? Linus Pauling draws out, basically he says this. He says, okay, water is hexagonal. So the way he draws this is the way that the water structure, the crystal structure of water looks like. I'm going to draw it in kind of a schematic way. And let me make this a little bigger, actually. I need a little space here. Let me get a proper square. Yeah, there we go. Okay. All right, so this is what we're looking at a bird's eye of the water crystal structure, the ice crystal structure. All right, and I'm going to draw the oxygen atoms as blue. Oh, sorry, so I'm going to draw them as, I don't want to use red because you guys don't like the red. Can you see this pink? Does that look okay? Yeah, okay, so this is oxygen. Right? And the circles, the smaller circles will be hydrogen in the red, in the yellow. Okay, I got to draw this out. Right? So in the middle of the lattice of crystal, there's an oxygen in the middle that accepts hydrogen bonds from 4 different oxygens. So there's a hydrogen bond here to a hydrogen that's connected to another hydrogen or another oxygen in the corner. There's a hydrogen. And then the next hydrogen, turns out, is in the corner of the lattice. Oh, sorry, this is a hydrogen, sorry. And that's connected to a water or an oxygen in a different lattice. I'm just going to use this as like a cut. There's a different lattice on this side. And it works like this. So you have another one. Yeah, like this. And then finally, one that looks like this. All right, so this is what the bird's eye structure of water looks like. All right, this is the bird's eye view of water, of IH ice. All right, it turns out that there's 2 different types of hydrogen bonds on a crystal, 2 different lengths. Okay, because so this one right here is so these 2 right here, the ones that are close. I should really draw these as the oxygens of the water, I'm sorry, and they're hydrogen bonded over to the other ones, I'm sorry, so that they go like this. Right? So these are the 2 hydrogens connected to that oxygen in the middle. Yeah, that's better. And they're hydrogen bonded to oxygens on the edge like this, okay? So you have the oxygen in the middle has 2 hydrogens, that makes H12. Here's another oxygen that have their own hydrogen somewhere else. And then this oxygen is also being hydrogen bonded to 2 waters on the other sides, right? So these are hydrogen connected to a different water. All right, so what are the distances here? Well, it turns out that in ice, the distance of an OH bond, right, the water OH bond, is 0.96 angstroms. Right, so this is 0.96 angstroms distance. And the distance for a hydrogen bond, which would be the distance between 2 oxygens, so the distance between 2 oxygens, is 2.76 angstroms. Okay, so the distance from here to here, bless you, is 2.76. And that means the distance from the far oxygen to the hydrogen, right, the length of that hydrogen bond is the difference between 0.96 and 2.76. That's going to be 1.80. Okay, so we have two different orientations. We have an OH bond about an angstrom, 2 of them. And we have an OH hydrogen bond around 1.8 angstroms, and there's 2 of them as well. Okay. So it turns out that the rules of ice are this, the ice rules. For each oxygen, two hydrogens, 2 protons, or hydrogens, I call them protons because that's what the NMR people call them, must be close and 2 far, and 2 that are far. Right? We just saw that. Right? And so what he argues is this. Pauling argues if there are N, which is N as in a number, oxygen 2 atoms, right? This is an oxygen atom of a 2- charge, and 2 times N hydrogen atoms, which are the protons, and these are the oxygens. Each OO bond, right, has 2 possible positions. Per proton. And therefore, there are 2 to the 2n possible configurations of the crystal. Okay, so now we look at just for the system of 4 oxygens. So for n equals 4, there are 16 possible configurations. Per oxygen, but only 6. And I won't argue why there's only 6, but Pauling determines there's only 6 possible that are favorable, that are physical. All right, e.g. that the hydrogen, what I mean by physical is that the OH bonds and the hydrogen bonds are preserved. Right, there's a bunch of different ways to arrange oxygens and hydrogens together that don't give you OH bonds of 1 angstrom and hydrogen bonds of the right length. You can put them in a bunch of random arrangements that don't make any sense. So there's only 6 that make sense, it turns out. Right, and so what Pauling argues is very, very clever. And I'm not going to go through the math of this, but I'll show you what he shows. He shows that W, remember that S is equal to KB ln W. It's the number of arrangements. You've seen this a million times. He shows that W is bounded by 2 to the 2n times 6 over 16 to the n power. Okay, he shows that. And so if you let n equals 4 here, S is equal to KB log of 3/2. That's what the math works out to for this equation. And that's exactly 3.4 joules per mole per Kelvin, which is the value, the discrepancy. So here's what happens. If you assume, now I don't expect you to understand this complete argument. I don't fully, so the math here is kind of weird, but it's just a statistical argument. So let me go back to the original values on the previous page. Right? Remember I said that we were off the ideal gas, the approximation from theory, which assumes that you have a crystal of 6 regular waters stuck together, right? That gives you an entropy of 188, and that's exactly 3.4 off from the real value. So what's the difference between reality and experiment? Well, theory says I'm just going to take 6 waters and compress them together, right? And the assumption there is that there is no entropy difference due to configurational differences. It just assumes that everything can go in together normally and that the statistics work out that way. Right? That there's no preference one way or the other for the waters to arrange. But in real ice, as I just showed you, right, so this assumes that you can put in 16 water, you can put in 4 waters 16 different ways, and you get this, you're off by an extra 3.4 joules per mole per Kelvin. So what does Pauling say? Well, Pauling uses the fact, right, what does this assume? Again, this assumes that the system is isotropic and homogeneous, right, it's spatially invariant, that you can just stick the waters anywhere you want, it doesn't really matter, they're going to freeze together, it's basically just 6 waters together, and we can just add the entropy of 6 waters together into form a crystal. But what this argument hasn't considered is the fact that the crystal takes specific orientations, and all of those orientations are different. They have different energies, they look different depending on how you cut them, and they have different properties, right? Because the solids are not spatially invariant anymore. Different arrangements of atoms in a lattice give you different energies. So what Pauling says is, okay, well, let's use the fact that this water can only take specific arrangements of the atoms in order to maintain the symmetry of the system, which is six-fold. It has this cubic-like tetrahedral structure. It's six-fold symmetric. And also you preserve the distances between the oxygen and its hydrogens and the oxygen and the hydrogens that are donating hydrogen bonds to it. That you have this alternating long, short. Right? That limits the number of possible configurations of the solid. Because as Pauling argued, there are 16 different ways to do this, and only 6 of them work. The others don't. And that difference between assuming all 16 work and assuming only 6 work gives you exactly that 3.4 joules per mole per Kelvin. Right? So this is a really good lesson, I think, about solids and why they're so complicated, is that you don't have the luxury with solids to assume that everything looks the same, like you do for a liquid or a gas. Right? You just take a little chunk out. It's the same material that the big chunk is. Right? Gases and liquids are like that. Solids are not, especially crystals. Right? Crystals have a very specific structure, and they have so little energy in them, they have to be in a low energy structure because there's no entropy to support them. Right? The system is going to relax as much as it possibly can, and there's a very limited number of ways for it to do it. And so what Pauling does is take that approximation, take that assumption, that things are no longer spatially invariant. We have to be careful about how to arrange stuff, and when you do that, you get the difference, the exact difference. Okay? So there's a couple of different other kind of intricacies in this as well. It turns out that you can make similar arguments about the entropy of a H3O molecule inside of water. For instance, one of the things that chemists do is when they do acid and base chemistry, they assume that the entropy of a solvated hydrogen, H+, right, so your H3O plus, if you will, has 0 entropy. Right? We define it to be 0. The entropy of a proton solvated in water is 0. But again, that assumes that the proton in water can take any arrangement that it wants. That it's spatially averaged, and it's spatially invariant, rotationally invariant, its presence in the water. So it doesn't really matter how you cut it. You're just always going to have the same density of protons in your water, regardless of how you cut it. And it turns out that that's wrong. It turns out that the actual entropy of a proton in solvated in water, like in an acid, right, HCl, like a mineral acid, is actually slightly larger than 0. Because hopefully I have a picture of this. I know I took a picture of this at some point. Ah, yes. So let me show you this. This is another little trick about water, and then I'll be done. So Orgo says that the entropy of formation of an aqueous proton, right? Again, that's like a Bronsted-Lowry acid, is 0. But spectroscopy shows that the entropy of formation of a hydrogen atom, of a proton, an aqueous solution, right, an acidic proton, is minus 21 joules per Kelvin per mole. The system orders. What that means is that H plus solvated is more ordered than the bare liquid. And why is that? Very strange, right? How does a liquid order itself around an H plus? Right? That means there has to be some new structures that form in the liquid that are ordering, that have some like defined structure, and that lowers the entropy. So this means that H plus forms ordered unique structures in the water. So that means that its density, its distribution, is not random and invariant. It goes backwards. It orders the water. Water with acid is more ordered than water without acid. And the reason why is really beautiful. It turns out that solvated protons form two different structures. Two different long-lasting structures in liquid water. And long-lasting in the sense that you can measure their infrared absorption, their infrared spectrum, which means they're spectroscopically identifiable. And I'll draw them for you. Two different types. And I'll use the same color scheme that I used before.
The next topic is cybersecurity.
One structure it forms looks like this. Right, so you have this H3O plus in the middle. Right, this is H3O plus. And it's hydrogen bonded to 3 waters. Okay, so this is the kind of classic H3O plus structure that you see. When you think about H3O plus, it's actually, the structure is actually 3 molar equivalents of waters around it at all times, stabilize the cation like this. This has a very unique name. It's named after it's a discoverer. It's named the Eigen structure. But it turns out that there's a simpler water structure that also forms in acidic water that is also dominant. So this is equilibrating with another structure where this extra proton is shared between 2 water molecules. It's another type of structure. And there's an additional water here as well by itself. This is called, after its inventor, who is still alive, the Zundel structure. Right, so these are long-lasting. And their time scale of their lifetime is about 10 to the minus 13 seconds. So they alternate back and forth very rapidly. So the rate of change is about 10 to the 12 per second. These are changing back and forth. But these are always existing. This equilibrium is always existing in liquid water. Right? So the water has formed this, around the proton, this ordered arrangement, this structure, this fixed structure that is alternating back and forth, but by and large it consists of one or the other. And this is an ordering process, right? You have these unique clusters, if you will, in the water. They're ordered, less, the hydrogen, the proton isn't just floating around randomly. It's stuck in these special clusters, and that brings these entropy lower than you would expect. It's an ordering structure. Just like we saw how water ice is lower entropy than you would expect because it's more ordered than you would expect from predictions. Okay, so water is very special in this way. 2 different examples of it. Okay, that's all I have to say today. We'll come back to, we'll start a new topic next class, equilibrium, and that will drive us to the end of the part once we get to kinetics, which will be in a couple weeks, and we'll be done. You guys have a good one. I'll see you Thursday.
I just have a very quick question
Yes,
for the
ma'am.
homework. Okay, for the very first one, I get why all the explanations for that.
Yeah.
For them setting up the thermodynamic
Yeah.
equations or something, like what in particular?
Well, all they need to write is
You can just write it on this if you want.
all I want them to write.
Okay. Okay. Okay.
That's all
Yeah.
we need to write.
Gotcha.
I forgot that you were still practicing. So the season is over.
That makes sense. I just wanted to like double check.
You'll see that
If you wanted to like. something more
1.2, it's clear where that equation comes from because it's just rearranged.
Yeah.
You'll solve that equation from DS and everything else. It'll be clear why I chose that.
Okay. Okay.
One thing that they need to realize that it wasn't immediately clear because Monica came in and she wasn't clear about it, so I think it's confusing, is that the membrane between the two compartments cannot exchange heat but can change material.
Okay.
So